Welcome back to lecture 11. This lecture is going to be on stacks and queues. We've spent the last 3 lectures talking about the list data structure, the list ADT, and the various implementations for it. What we're going to be looking at now are 2 ADTs that are in that small category of ADTs that do tend to have specific restrictions. We said when we talked about the interface decisions for a list that there is no set-in-stone list class, and there isn't necessarily a set-in-stone stack or queue class. Ultimately, you can do whatever you want. But typically, when we talk about a stack or a queue, there are certain restrictions we're discussing in terms of not so much what you can do, but rather what you can't. And so those tend to be far more standard than, say, whatever the list interface would be, or whether the whatever the tree interface or array interface might be. And we will start by discussing stacks. The idea behind a stack is one, if you've seen the abbreviation LIFO, which stands for last in, out. That is a stack structure. The concept here is that you have a base to your stack, and as you add elements to it, you're repeatedly adding new elements on top of the other ones. So we have here 5, 7 added on top of that, 3 added on top of that, 2 added on top of that, and so on. And we're always keeping track of where the top of the stack is. And so since we're always keeping track of where the top of the stack is, that means that's the only element we can read. We'll be able to read that element. We can add onto the top of the stack. We can remove the element from the top of the stack. What we can't do is dive into the middle. Any more than, if you're in a cafeteria, you can remove the top tray, or maybe you decide the food's no good, and so you put your tray back. But you don't pull trays out of the middle and let everything collapse. And it's the same thing with linked lists, or with stacks. We have the elements definitely in a linear order, so we'll be able to use a linked list to implement it. We'll be able to use contiguous memory to implement it as well, and we will look at that in a second. But the idea is all these structures we've been looking at so far are linear based. The array is linear. There's a first, a second, a third, a fourth element. The list was linear. The stack now is linear as well. There's a definite order to the elements that doesn't change. A particular element has a set-in-stone predecessor and successor. And the same thing will be the case with the queue. So all 4 of these structures, the array, the list, the stack, and the queue, all these ADTs could be implemented using both the linked implementation and the contiguous implementation. Now, up to this point, we've seen the contiguous implementation of the array class, and you might be thinking to yourself, why on earth would you ever use linked memory to implement an array? We will, in fact, see situations where that actually is done in the next lecture on sparse arrays. We analyzed the contiguous versus the linked implementations for the list ADT, and today we will look at contiguous versus linked implementations for both the stack and the queue. And so you'll have basically these 4 linear-based structures: arrays, lists, stacks, and queues, and you can implement both of them either with linked or contiguous memory. So you've got a lot of options here. But as far as what the stack ADT tends to be, or the collection of operations anyway, we typically have 4 operations that we worry about. We have the idea of push. This would be the insert. We're taking X and we're pushing it onto the stack, which means we put a new element on the top. We have the idea of pop, which is a return and remove. We will remove the top element from the stack and send it back. We can also read it without removing it, and that would be top. So in that case, we would send it back without removing it. Running pop on this stack would remove 2, send it back, and 3 would be the new top element. Running top on the stack would send back 2, but 2 would still be on top of the stack. We'd return a copy of 2 so that you know that 2 is the top element on the stack. And then because you don't want to run pop or top on the stack that has no elements to return, you would typically have an isEmpty function as well, where that you can use bool here too, but bool has only been recently added to the C++ language and isn't always standard built into compilers. So often you'll still see integers used for booleans, where you return 1 if you mean true and 0 if you mean false. And that was how things were done before the bool type was added. Now, sometimes you'll also see an isFull function if you have a preset size for your stack. For our purposes here, we'll be assuming the stack can grow as long as you have computer memory to hold it, so we're not going to preset it to size 20 or 30. If your class did that, you'd have an isFull function. Likewise, depending on the language you code in, you may have other functions as well. C++ will probably have a default constructor, may well have the big three as well. And so, again, the idea is the ADT, even with stacks, is not set in stone. You might have a size function to return the number of elements in your stack, or you might not. What you tend not to have with stacks, and this is generally the definition of stack, is you usually are not able to read the elements, and you're definitely not able to alter them. So this is the only element you can alter. If you had some sort of function that printed the entire stack, that may allow you to read things a little bit. But typically you can't read or write the other elements, only the top element, and that's the general definition of a stack. The last in, first out, so as you dump things in, the last thing you dumped in is the first thing to be removed, and it's the only thing you can currently read or remove or add on top of. So that's a stack. And so the question now is, how can we go about implementing this? I mean, there's not a whole lot more to say about the ADT other than this tends to be the standard ADT for a stack. Those are the four critical functions we will worry about. And let's consider then an array. How would we go about implementing the stack in an array? Let's consider a large array like this. We have perhaps here cell 1, cell 2, cell 3, cell 4, and then we have here, say, n minus 3, n minus 2, n minus 1, and cell n. So we have there an array, and the question is, I have this stack from the previous slide. How would I go about implementing that stack using an array? Where would I put these values? And we may notice one thing, which is that if we're going to be inserting on the top, we'd like that area to be free. So if I'm going to write here 2, 3, 7, 5, and put the bottom of my stack here, that means when I want to insert on top of 2, I'll need to scoot everything over to make room in A of 1, where this, this array, assume we call A. On the other hand, if I put 5, 7, 3, 2 here and have my top on this end rather than here, then I don't need to shift things over to make room for a new top. Instead, I simply write in the next available cell. That is, if I let my stack grow this way, I then can start adding new elements in the available cells and remove elements from those cells as I need to, as I pop from the stack. So let's arrange the stack. We know the bottom isn't going anywhere. We can't remove 5 until everything else is gone. Let's stick 5 way at the beginning of the array. And let's point the growth area of the stack in the direction where there's memory to grow, rather than putting it in the opposite direction, having 5, 7, 3, 2, and then having to shift everything over to stick something above 2. That would be linear time. Doing it this way, it's constant time. Typically, we will also have an index indicating which cell is top, and then we would manipulate things using that index. So for example, if I'm going to write out the push function, and again, I'm not scoping this to the class, I'm just writing out the rough pseudocode here. I can say here, if I want to add a new element, I increase top, in this case, to 5, which would give me perhaps that cell. And then I can say A of top equals X. So if X was 6, then I'd be writing 6 into that cell. And I've just now pushed 6 onto the stack. Likewise, we can consider then what would be involved in a pop. And we can say, well, all that would really be involved here would be I could save this value. I could say eType temp equals A of top. So now temp would hold 6. Then I can say top minus minus, so it's exactly the opposite here. Copy the value from A of top into some temporary variable, decrease top, and then I could say return temp. Now you might look at that and say, that seems like an awful lot of work for nothing. And you'd be right. I want to do the long version first and illustrate what we're doing here is we're saving 6 somewhere and then eliminating that memory from our consideration by decreasing top back to 4 and then sending back to 6. But in reality, just because we decrease top does not mean we've lost that cell. If I call delete on something, then it's lost. But if I'm decreasing top from 5 to 4, I still have A of 5, as well as A of 6, and A of 7, and A of 8. All I've done here is ensure that for the current state of my stack, I view 4 as the top element, and therefore will never read A of 5. But A of 5 is still allocated, the 6 is still sitting there, and there's nothing keeping me from reading it. So if I wanted to rewrite that function, I could just as well have said have a pop function here. I could just as well have said top minus minus right off the bat, and then said return A of top plus 1. There's a few other ways I could have written that too, but at the very least I could do things that way. And I could say, well, I'm going to decrease top from 5 to 4, and then, oh, top plus 1 is what used to be the top, send that back. Because even if top is decreased to 4, A of 5 is where the old top value was, and that's what we want to return. There's no harm in doing this because this is not freed memory. It's memory we're not really using in our conceptual view of the structure at the moment, but it's not freed memory, and so it's safe to read. Unlike addresses of local variables that are part of functions that are dead, as we talked about in lecture 4, or the idea of reading deallocated memory. Those kind of things you don't want to do, but this is safe to do. And so instead of doing the long version, you could have done the shorter version as well. For the linked list, we'll need the longer version, and we'll see why when we get to that point. Other than that, there's not a whole lot to say. The other two operations are relatively straightforward. If this is our class, then I can simply say for top is just reading the current element. It's not removing it, so I can just say return A of top. And that's basically the same as the retrieve code for the array implementation of linked list, where I would basically say return A of current. Now I'm saying return A of top because top marks the current element. Same idea. And then for isEmpty, what I need to do is figure out what would indicate that the stack is empty. And certainly if top is 2, then that means I have 2 elements, 5 and 7. If top was 1, I'd have only 1 element, 5. When I pop that, top will be reduced to 0. And so the signal here that the stack is empty is that top is equal to 0. And so if this is true, we return true. If that's false, we return false. Because whether or not the stack is empty is equivalent to whether or not top is 0. And that's because our first index was 1. If our first index had been 0, then top equaling -1 would have been the check for emptiness or non-emptiness. So it's always whatever is 1 less than your starting index. So that's the stack functions. There's the 4 of them. And it should be clear they're all constant time. Each of these is definitely constant time. It's just one line, one array access, one comparison. Push and pop, that's just an increment and an array access and a write. This is just an array access and a decrement and such. So there's nothing here that depends in any way on the size of the array. All these things are constant time. However, there is one interesting issue to deal with here, which is that push is not exactly correct. Because it's possible that as I add to my array, I basically run out of room. I could have had a situation here where this is my array A. So we have, say, A as a pointer to an array. And I fill in my last cell, and now everything's filled up. And the next push operation I might want to do now is not going to have any room, and it's going to need to trigger some sort of a size increase. We may say, oh, the stack's full, too bad. But if we would like a stack that gives the illusion of growing to whatever size we want, then what we would need to do is have a size increase. And you can certainly control how large the stack would grow, and in terms of the size being allocated for it, and most stack collections that would grow automatically would provide you with that control, similar to the set balance function in the array class you looked at in section 2. But in the absence of any other information, the default is to double the size of the array. So if I have n elements here, and now I need more space, the default generally is to double the size of the array. So this would now become 2n. And there's a reason for that. The idea here is keeping in mind we can't just increase the size of the array. The array needs to be contiguous memory, and this memory, when we created the array of size n, we could have gone ahead and used this memory for something else then. And so as a result, we have no means of guaranteeing that memory is available for our array, and therefore the language can't provide that facility to just, increase the size of the array without a problem. Instead, what has to be done is we have to allocate a larger array somewhere else, copy the individual values into the larger array, and then perhaps call delete A and get rid of this, and then point A to the new array, which would have been pointed to by some other, we would have said initially that temp equals the new array, temp equals new whatever, and then copy each of these into here, and then delete A, and then A equals temp. And hopefully you've seen something like that before in an earlier programming class that dealt with arrays. But if not, now you have. So the idea here is that we can't just increase the array. We need to declare a larger array, copy the old values from the old array into the new one, and then we can get rid of the old smaller array, and we have all this extra space. So we copied n elements, and we have n elements left here. And the idea here is as follows. If I had instead increased the array only to n plus 1 in size, since I'm copying values one by one from the old array into the new array, the copying is going to take order n time, no matter what the size of my new array is. If the size of my new array is n plus 1, or 2n, or 5n, or 200n, I'm copying n values into the new array, and the rest of it's all dead space, whether it's 1 extra cell or n extra cells. So I'm copying n values from the old array to the new array. That will take order n time. So we're stuck with this order n copy no matter what. When it's time to increase the size of the array, that'll be an order n operation. The question, however, comes up, how often are we going to need to do this? And this is what brings into the idea of amortized analysis. We're not going to really worry about this term too much, but I'm at least going to throw it up here so that you're familiar with it. And the idea is more or less a long-term analysis. Instead of worrying about the individual running time of a single operation, what we're saying here is if we have a collection of operations run one after the other, take the total time for all those operations together, divide by the number of operations, and what's the average running time for one of them? Or in other words, let's describe the running time in terms of all these operations at once. And so note that if we go from size n to size n plus 1, we'll have an order n copy to start things off. Then we will get to do an order 1 push. And right away, then the next time we do a push, we'll have to do an order n copy again. Because we will just pushed into, we try to push into this cell, but it's the array's full. So we make an order n copy, we make a copy in order n time, adding one cell that we write into, and now the very next time we try and push, the array's full again. We have to do an order n copy. Which means that we're going to tend to have an order n copy associated with every push operation, and so after n push operations, we would have n times order n copies, and n times order 1 push operations, and that ends up being order n per operation. So because this is going to be n squared plus n, the n squared time for all these copies, all these expansions every push operation, plus n time total for all the push operations. Or in other words, we're basically saying these two together make up a push. Increase the array by one cell, do a push. Increase the array by one cell, do a push. And so each push can be thought of as taking a linear time. And that's in stark contrast to the idea where we say we have n, we end up with 2n. I'll have to do this order n copy, but now I'll have to do n pushes at order 1 each before another resize is needed. And that's the key idea. If I double the size of the array, then what happens is I'm able to do n more push operations at constant time each before I need to resize again. Up here, I needed to resize after the very next push. Here, I can get away with n pushes before I need another resize. And since those n pushes take linear time total, who cares about the resize? If I'm doing a linear resize after doing a linear time collection of operations, constant time pushes, but n of them are done, then it basically gets hidden. You've got a cost here of increasing the size of the array, but we say, okay, I increased the size of the array, I took in linear time to do the copy, and then before I need to do another copy, I've got a collection of operations that adds to linear time anyway. So just add them together. I've got 2n instead of n. For the collection of push operations. Here, the collection of push operations took n squared time because we were having to do an order n expansion after each push. And so if your collection of push operations take n squared time, each one takes order n time. Here, the entire collection of all the work takes only linear time. One expansion or one copy and a bunch of pushes. Total is order n plus order n is order n, which means each operation is about constant time. You've got n pushes and one resize divided into n order n time. Each operation comes out to constant time again. So the idea is by doubling the size of the array, you're saying I'm going to ensure I have to do a lot of push operations before the doubling has to happen again. So you're trying to reduce the frequency of the doubling. And of course, by making the array 3 or 4 or 5 times as larger, you'd reduce the frequency even further. Doubling is a happy medium. You're not allocating gobs of extra memory, enough extra memory that your next array increase won't occur too soon. And so in the end, then everything works out to basically an average of constant time. So that's why we don't really need to worry too much about the array expansion. Yes, the array expansion would need to be coded and would need to be dealt with, but it would only happen every once in a while because we'll double the array each time. And therefore, it doesn't really factor into the running time to any great extent. Now, that's a tough concept, so if you're having trouble with it, by all means, you should get a hold of us and ask us about it. But that's the idea of why we would double the size of the array rather than just increase it by one cell, because it means we can put off doubling again longer, as opposed to having to double again at the end of the next operation. So that basically is all there is to say about the array implementation for stack. The length implementation for a stack, you have similar issues to worry about. If this is our stack again, 5, 7, 3, 2, then our worry here is to say, well, do I want to implement a list that looks like this? Or do I want to do one like this? And position the top, do I want to position the top of the stack at the front of the list or at the end of the list? And the answer should be motivated by a couple of things. One of them is, well, if we deal with a singly linked list, removing from the end of a singly linked list does not work well unless we have a dummy node. And so since I'm going to be removing this element, I may as well position things in the front and say this. Head points to 2, points to 3, points to 7, points to 7, points to 5, and of course that points to null. Now I could have done things the other way as well by using a dummy node. So I mean, I could have said in this case, let's say I have here head, and I'll have here 5, 7, 3, 2, dummy node, and now I can remove 2 very easily by doing that little remove trick. But why? If I can do things here without a dummy node, why would I do things here with a dummy node? Plus, of course, I would need a permanent tail pointer position there to always let me know I'm at the end, so I can insert or remove there. Or I could use a doubly linked list, a tail pointer with a doubly linked list, so I could remove easily, or a tail pointer with a dummy node at the end, again, so I could remove easily. And why would I take up the memory needed for a tail pointer and a dummy node, or a tail pointer and then pointers for every other node, when the singly linked list works just fine? I can remove or add to the beginning of the list very easily. So yes, I could put the top of the stack at the end of the list and make things work. But to make everything work in constant time would require first a tail pointer, so I always know where the end of the list is. And secondly, would require either a dummy node, so I can make sure remove works in constant time, or a doubly linked list instead of a singly linked list, so again, remove would work in constant time. And you look at this and you say, well, I get constant time, insert, and remove with that situation without using a doubly linked list and without needing a tail pointer and without needing a dummy node. So why wouldn't I do that? Yes, the doubly linked list use of memory is not that big a deal, but if the singly linked list provides exactly what we need, why waste the memory? It's not a severe waste going to a doubly linked list, as we talked about last time, but it's still not worth, if all else is equal, don't use memory you don't need. And here, I can get away with a singly linked list without a dummy, without a tail, so let's do it that way. And let's set things up like this. That's the best way to go. We could do it the other way, but it would require more memory resources than we need. So why not use, all else being equal, if you're going to get constant time performance from both this and this implementation, then choose the one with less memory. And that's this one here. So what we'll do is have the top of the stack at the head of the list and the bottom of the stack at the end of the list. And as we push onto the stack, we'll increasingly add elements to the front. And as we pop from the stack, we'll remove elements from the front. So that means then that, let me write this up here, head 2, 3, 7, 5, and null. And if I'm going to have the function top, well, that's easy enough. I simply just return head arrow element, the element in the head cell. And if I want is empty, well, is empty would be in a case, int is empty. That would be used in a situation where I had no dynamic nodes because I had nothing in the list. And so in that situation, I can simply say return whether or not head is equal to no. If head is equal to no, I would return true and say, yes, things are empty. If head is not equal to no, I would return false and say, no, head is not empty. So those are just sort of one-liners. Clearly, they're both constant time. Everything's cool. Now what I want to do is look at push. Push is simply just making use of the idea that I say, well, I need to create a temp node here. So I can say node star temp equals new node x. So I can see that down here. Let's create a temp pointing to a new node x, new node holding x. Then I can say temp next equals head. So that would point to 2. And then finally, head equals temp. And so head would stop pointing to 2 and would point instead to this new first node. And now we've inserted on the front with just those 3 lines. It's the same thing as inserting into anywhere, inserting after. I make my node point to the thing I want to be before, and then I take the pointer that comes before me and point it to me. It just now, the pointer that we're doing here is not current next, it's head. But otherwise, this is basically inserting after when we looked at that code. It's pretty similar to that. Create the new node, and then set the next, and so on and so forth. As far as pop goes, pop is interesting, because if we've got this list set up now, if we've got this set up here where I say head, and let's say we have 1, followed by 2, followed by 3, followed by 7, and so on and so forth. Now notice as far as pop would go, I can't just say, well, point head to 2, because then I leak memory for 1. So we need to at least delete this, and so I can say, well, here's E-type pop, and I can at least say here, well, I'm going to have a node pointer temp equals head, so I'll point a temp to here. Then I can say head equals head arrow next, and that would point this over here. Now I have the ability to say delete temp, and that gets rid of that node. And so we haven't leaked memory now, so I can't just say head equals head arrow next, though that's kind of what I'd like to do. I first need to point a temp to that old head node, so that when I move head, I can then delete temp and get rid of that node. But that still isn't enough because I need to return what was in there too, and I can't go reading that value anymore because it's in a deleted node. And I can't put the delete after the return statement. I can't say return temp element and then delete temp, because once you hit the return statement, you're done. The deletion has to happen before the return, but I need to return what's in that node. And so my only real option here is to set another variable aside, eType x equals head element. Read the first element, store it in x. Now I can delete the first element safely, and I've had this 1 stored somewhere else. And then I can return x. So that's what's involved with pop. The idea is that I can't just say head equals head arrow next because that would leak memory, but I can't just deal with head equals head arrow next and the deletion of the memory because I need to return what's in that node. And we have this sort of interesting contradiction where I need to delete this node before I can return its value, but I'm not supposed to be reading its value for returning after I've deleted the node. And so the answer is to say, well then, fine, I'll read the 1 out of that node before the node's deleted, but I'll return that value after the deletion when it's stored in a different variable. So instead of trying to say now return temp arrow element and hope that it hasn't been reclaimed yet, which would be very dangerous, instead I'll just grab this value and store it elsewhere, then it's safe to delete that, and then I can return that elsewhere storage. So that's clearly constant time as well, and that's all there is to say about the stack implementations. We've looked at the list implementation, we've looked at the stack implementation, and that's, we've looked at the list and the array implementation of stack, and everything was constant time for both situations. The summary comments I'll make at the very end of this lecture will discuss this more subtle differences between the two implementations, but basically the array and the linked list will work relatively equally well because you've got the idea of all 4 key operations work in constant time, regardless of the implementation you pick. And as far then as that goes, a queue, when we deal with a queue, is nearly exactly the same discussion. Very few things will change, and so we can very quickly go over queue in far less time than we talked about a stack. When dealing with a queue, basically this is a line, going into a line at the bank, or the analogy I always like to use is a car wash. Partly because my drawing is hideous, and so students in class usually laugh when they watch me draw my cars, because I can't draw cars to save my life. So go ahead and laugh. I can't hear you. So a car wash, I think, works very nicely as an analogy for queue. You often see the abbreviation FIFO for queue, which stands for first in, first out, because the first car and the first person to get in line is the first person to be handled by a bank teller. The first car to enter the car wash is the first car out of the car wash. But most importantly, you don't tend to have a car suddenly rip through the car wash and drive off. Once you're in the car wash, you're in until you leave. And so our general model of a queue as far as information goes is we have the front of the queue and we have the rear of the queue, and we'll have, say, data here, 6, 2, 1, 5, and we will add new information on the end of the queue, 0, 9. We will add, cell by cell, add information onto the end of the queue, and we'll remove things from the front. So it's just like a stack in that you are allowed to read a particular element, only one element, you're allowed to remove only one element, and you're allowed to insert only in one place in the structure. The only difference is that in a stack, those 3 were all the same spot, and in a queue, the reading and removing happens at the front, the inserting happens at the rear. So you would deal with 2 different ends with the queue. But the functions are the same. You can say here void onQ, which is the equivalent of push. OnQ will insert a new value onto the end of the queue. You have eType dequeue, or dequeue, depending on how you pronounce it. And that's the equivalent of pop. You remove the front element and return it. The equivalent of top is front, as well you might expect, because we always talk about the top of a stack, so call the read function top. We're talking about the front of the queue, call the read function queue, or front. That will read the front value but not get rid of it, unlike dequeue. and then we have our is empty. So we have an exact parallel here to stacks. We have, instead of push, pop, top, and is empty, we have on queue, day queue, front, and is empty. But there's an exact parallel. The only difference is on queue and day queue work on different ends, on queue and front work on different ends. Where for a stack, they all worked on the same end. So if we consider implementing this using a linked list, we now have to consider, well, again, let's try and think, can we use a singly linked list in this case, or are we forced to use a double? And in this case, since the operations are on opposite ends, we have to use both ends. We can't stick everything on one end. And so the concept to think here would be, well, I can insert from the front and remove from the end, but removing from the end is linear time. Or I could insert from the end, or at the end, remove from the front, and then both of those should be constant time. So if I have a queue here that looks like this, where I have here 5, 7, 2, 3, and this is the front, and this is the rear, I'm removing from the front. The way I would set up a linked implementation would be I would have the front element as the first element. And then I would have here, I'd insert onto this end, remove from that end. That way they both work in constant time. And you think, well, how can they both work in constant time? Well, in fact, all the operations work in constant time. 3 of them will be exactly the same as the stack implementation using a linked list. If I have no values at all, I know things are empty, so if head is null, that's the signal that it's empty. If I want to do run front, that's the same as top. Just return head arrow element, the element of the first node in the list. And if I want to do a day queue, that's the same as a pop. You're deleting the front element of the list, so that same five lines of code we use to run a pop, we would actually use to run a day queue as well. And the only difference is on queue, because for a stack, the push was pushing on the beginning of the stack. For on queue, it's adding to the end of the queue. And the way to make this most efficient would be to have a tail pointer sitting up here, and then all the onQueue function would need to do, we have eType x. OnQueue would simply say tail arrow next equals new node, pass an x, and then tail equals tail arrow next. So we would say point this to some new node, which itself points to null, and then move tail to there. And that's all that's involved in onQueue. As long as you have this tail pointer, that's it. We don't need a dummy linked list. We don't need a dummy node. We just need a tail pointer. So of course we need a head, or we lose the linked list entirely. In addition, there is exactly one memory cell of sort of extraneous information. We need the tail pointer to make things work quickly. So that's not too much. One cell is not too much memory to be using to make things work in constant time. So that's the linked implementation of a queue. The array implementation is a little bit more interesting, because we have this idea here of, well, I can have, certainly if I put the line up the rear of the queue here, every time I insert, I'm going to need to scoot things down. So I'm better off saying line up the front of the queue here, line up the rear of the queue here. Now as I day queue values, I lose them, and eventually front's pointing to here. Likewise, I can onQueue values to the end, and eventually rear is pointing here. And what will be happening is that we start out with our queue in these spots. After a while, the queue is in these spots. And little by little, as I add elements to this end and remove elements from this end, the queue has shifted down into the end portion of the array. And now I've run out of space. I have no more room to onQueue something new. And I don't want to say, oh, just increase the size of the array, because then I've got this huge, vast amount of space in front of me for the queue to just keep shifting. Not using, but shifting into, leaving a huge mess of wasted space behind it. I'd prefer to use this space rather than just let it sit there wasted. And the way we would do that is by using a circular array. The idea being here, if we have an array from 0 to 6, we will picture it as 0, 1, 2, 3, 4, 5, 6, and picture it more or less like a ring, where just as cell 5 logically follows cell 4 and cell 6 logically follows cell 5, cell 0 logically follows cell 6. Or in other words, when I want to on-queue a new value onto the end of the queue, I don't have room to do it here, so what I will do is I will come over here and write it. And this would be the front. Rear would move from here to here, and that would be the rear of the queue. So we have element 1, 2, 3, 4, 5, and these would be the various elements of the queue. The very last one would be that one there. And as I deleted elements from the front and added them to the rear, the queue would start to look like this, where you have your front portion here, your rear portion here, and this is logically right in front of that. So in a sense, we allow the queue to wrap around from the back to the front of the array, like, you know, a giant Pac-Man game. And the way then this would be done would be using the modulus operator. Rear equals rear plus 1, and that would normally be what we do is, in terms of creating the index, rear equals 1 to the right of the rear, but now we'll say rear equals rear plus 1 modulus the size of the array. And so we'd say here, well, 4 plus 1 mod 7, if the array goes from 0 to 6, the size is 7. So if your rear is 4, 4 plus 1 mod 7 is 5. So 4 moves to 5. 5 plus 1 mod 7 is 6. So 5 moves to 6. 6 plus 1, which is 7, mod 7 is 0. So from 6 you move to 0. And so you'd have a similar equation for front, but basically as your rear pointer moves, when it moves up the end of the array, it wraps around the beginning. And that's how you get these situations where you can say, here's my first, second, third, wraparound, fourth, fifth, sixth, seventh elements of my queue. And setting it up that way, then you are able then to have the queue, all the queue operations work in constant time in an array. And I'll leave those as an exercise for you using these ideas. But that's basically what goes on. And so that's it. We can then, for both stack and queue, we can use either the linked implementation or the contiguous implementation. Both of them will enable the all 4 key operations to run in constant time for both implementations for both ADTs. And so as far as choosing between list and the contiguous implementations, it's just those subtle differences we talked about before. One we haven't talked about before. Certainly the array implementation uses less memory, but it also doesn't grow as gracefully. And so if you're going to have an array of exactly the right size, it uses the least memory, but you'll probably have more than the exact size because you want room to grow, and so it may waste a bit of memory. On the other hand, it's very fast because your cells exist already, where the linked list, every time you do a push or a pop or an on-queue or a day-queue, needs to allocate or deallocate memory, needs to call on memory manager functions, and that will chew up a tiny bit of time. Where with the array you do one allocation, and then you have a bunch of cells to grow into without having to dynamically allocate values every time. So there is a bit of a speed versus memory trade-off going on in there. There are reasons to use the array like that, and there are reasons to use linked memory. And but they're far less clear than the very clear decision to use linked memory for the linked list. Here the differences are very subtle, and in many situations those differences would be so subtle that it wouldn't really matter either way. But anyway, that's all there is for stacks and queues. The next lecture we will be dealing with will be on sparse arrays, where we will be dealing with different implementations of the array ADT that are more designed to save memory than to make things run quickly. And so we will pick up there when we come back, and see you then.